Right, good day everyone. This is Jason Strait with the Cloud Pass Virtual Group. Our presentation today is using Columnstore indexes in Azure DevOps Services, lessons learned. Our presenter is Konstantin Kosinsky, and he'll be taking over here in just a moment. I just have a few announcements that I want to go through before we get started. So the first thing is that if you are not currently subscribed to the Cloud Pass virtual group, I do recommend going out to cloud.pass.org and taking a moment to log in to the site and then subscribe. The biggest value in doing that is you find out when all the presentations are, but then also if there are any rescheduling, you get an opportunity to do that as well, to get that information as well. Over the next few weeks, we've got a number of presentations coming up. We've got about 12 on the calendar right now, and if you note the ones that are in orange, the IT governance and the Azure SQL PaaS and the DevOps with Azure containers, those are all new sessions that were just added in the last few days. So you probably haven't had a chance to go out and register for those. So do take a moment to decide if you want to do those and go get registered. If you are interested in presenting to our virtual group, I do recommend just emailing us at cloud@pass.org, or if you don't want to do that and you just want to fill out a form, you can also do that at cloud.pass.org. There's a Cloud Virtual Group call for speakers. Click on that link and you'll get a form that you can fill in and get the information, and then we can get you scheduled. Coming this fall is PASS Summit 2019. Just a couple weeks ago, they announced all of the community call for speakers sessions, and so you can now go out and see everyone that's been approved to speak, and you can see what topics are available for this fall's summit. If you have yet to register for the PASS Summit, you can get a discount through this virtual group. The discount is available by just typing in VGDIS-FKDQ as you're registering, and that'll knock off $150 US from your registration. This virtual group is part of a number of virtual groups that PASS supports to help people learn more about data platforms on Microsoft technologies. So if you are interested in other topics, there's some focused directly on different languages, such as Global Hebrew and Global Italian. And there's others that focus on different technologies and job roles, such as the PowerShell and the data science virtual groups. All of these virtual groups do record their sessions and make them available on PASS TV. So you can go and look and see what's coming up, and you can see what has already occurred. Throughout the session, you may have some questions. If you do have questions, please type them into the question panel within the GoToWebinar application. At the end of the session, we will go through all those questions, time permitting, and give Konstantin an opportunity to respond. And with that, that is all of the announcements that I have for today. And so our session again is using Columnstore indexes in Azure DevOps Services, lessons learned. And our presenter is Konstantin Kosinsky. So at this point, I'm going to make him the presenter. All right, there you go.
Okay, hi, can you hear me and see my screen? I hope yes. Yeah. Okay, can you hear my? Can you hear me and see my screen? Yep. Okay, so my name is Konstantin Kosinsky. I'm working with Azure DevOps Services at Microsoft, and today we will talk about what lessons I learned when we are using Columnstore indexes for building the services, what problems we saw, and what suggestion I have for people who try to build something using Columnstore indexes with SQL Server. Before I joined Microsoft, I was SQL Server and Data Platform MVP, and now I'm working with Microsoft for 12 years. So to provide a bit of context what this service is and what requirements we do have for data storage, I will explain what's analytic services. So if you're using Azure DevOps, you need to you want to report on some data about work items like stories, bugs, or your CI/CD pipelines, or about automated tests and manual tests. So a service that I'm working on is collecting all this data from different parts of Azure DevOps and allow people to build some experience to it. So we do have some in-product experience that is set of charts that show you lead cycle time, your burn down, your velocity, some stuff about your test performance, your build pipelines performance. It shows you how many failures you have, how many test successes, and you can drill down into this information. If you are more to exploratory analysis, we do have Power BI add-in that allow to people to just export data, load in Power BI, and do reporting their own. Internally, it's just OData. What OData is, it's query language over HTTP when you can say, okay, I want my work items, I want only these columns, I have this set of filters, I want only that set of columns, I want to follow some navigation, for example, like I'm expanding for assign to, so I can see like who is developer working on this stuff. And you get a response as a JSON format. So all our experiences is work like support real data. As a result, if you want to build your own reporting or something like that, you can just use OData for that. And a good part with OData, you can use aggregation extensions that allow you not only like give me this set of data, but ask server to aggregate all this data on the server and just return you an answer. Here's a sample when I'm aggregating my test runs by date and do a different type of calculations. So, and I'm getting that as a JSON. So when we start building this service about 4, maybe 4.5 years ago, we started thinking what query system we will use, and we did have a big set of different requirements. First of all, we need to deal with a huge amount of data in millions of records. For example, for our test results information, we do have some accounts that add about 100 million test results a day, and in good days it can be 500 million. So we need to deal with this huge amount of data. And most queries are aggregation queries that need to return one number on after aggregating the millions of records. And because we're a reporting service, we cannot allow, have a very strict set of APIs that allow answer only questions that we are. I think people will ask, we need to allow arbitrary filtering aggregation group by, so our users or other developers who build on top of us can build whatever they want. We need to our storage and storage system should support updates and deletes, because we do not allow it to, let's say, take a big ETL window when during night we are processing data and you have your result on a date. Plus, any data can arrive a bit later. You can see your test results first, and then only after that see in which build they happen. So we need to deal with that. Plus, any software has a bug, so sometimes we need to fix a bug and do modifications in data to deal with that. We need near real-time ingestion and availability of new data. So far, if you just modify it, like your bug, reassign to a new person or close it, we show it will be available in the service in a few seconds, so you can report on it right away. We still need to support on-premise installations, and a trick with that is that most of great cloud-only technologies were not as a result was not available for us, so we need to stick for something that's available on-prem only, on-prem too. And yeah, we are a reporting solution that people understand that reports can be can take a long time to to generate. But if we have this widget that show you how many bugs you quoted this day, people will not tolerate if it's take more than second or something. So we need sub-second query response times for that. And being a service, as a platform as a service, we couldn't afford maintenance to say people, oh, we're adding new table, we're modifying the schema, so all database maintenance have to be online. And on top of all of this, we need reasonable how expensive it will be to maintain the system. If we go, for example, with SQL database, I couldn't give the most performant database for every user. It will be just prohibitively expensive. To satisfy all these criteria, so we start working on Columnstore indexes, and doc says that they provide a great compression. It can be at least 10 times more than when you have just raw storage. They are optimized for database warehousing queries when you're not looking for single record or few records, you're looking for aggregating a lot of records. They allow you not to create separate index to maintain each query shape, and we can just have one Columnstore index and be satisfied all reports with that. And starting with 2014 version of SQL Server, and more with 16 and 17, and now it's with 19 and Azure DB, its support for updates are increasing, and we can do small changes on the fly. So let's look how Columnstore index is designed, so we can have our next steps more. Can you hear me? Because it says that audio connection has been lost.
Yeah, I can still hear you.
Hey, can you?
Yeah, it's coming through fine.
Yeah, okay, because it was saying that it's like connection lost. Okay, so how Columnstore indexes works internally, so we can do more like dig in details and look on different features. Let's assume I have a table with 6 columns, like from C1 to C6, and Columnstore indexes organize data in row groups. Each row group is about 1 million records. It can be smaller, but it cannot be more than 1 million rows. And in my schema, they are in my slide they color-coded orange is 1 million, and red another million, and another orange is 1 million. Each column in each row group stored separately, and it's called segment. So if we have this C1 column, 1 million rows, it's stored in separate segment, and it's really compressed. It will not be exact definition how it's compressed, but you can think about this. Imagine you have a price or total amount of something for your sales. Instead of keeping a 1 million total values, it keeps only unique values, and for each of these unique values, it says, oh, this one is 100. Total amount 100 was used 17,000 times, 200 was used 15,000 times, and stuff, and so on. So as a result, if we have query like this, I want to sum column C1 and column C2 for my tables. Because each column are stored separately, when SQL Server executes this query, it can completely ignore C3, C4, C5, C6, and just focus on these columns. It's called segment elimination. Another good part here is that instead of unpacking all these million records in each segment and then aggregating this, SQL Server is able to do aggregation on already pre-compressed data. If you have a million, if you need to do million sums, it's one performance. If you need to, let's say you have segment with 100 unique values, for each you have how many these unique values used, it will be 100 operation to do this calculation. Another stuff, let's assume I have some filters. They say, for example, column C4 greater than 22. In metadata for each segment, for each column, for each row group, we have a stored metadata that says what is the mean and max value for that column in this segment. As a result, if I have this for C4 and I'm looking for where C4 is greater than 24, I could skip another, like, two row groups skip completely and deal only with this one row group with this three segments. It's, again, segment elimination. It allows to read much less data when we query it. So here's how, on very high level, how Columnstore indexes works. And to make them performant, it's like 5 pillars of this. Segment elimination, we was talking about this. Another one is a predicate pushdown. What is a predicate pushdown? It's ability of SQL Server to push down a predicate to a storage engine and do filtering on pre-aggregated, on already aggregated data. Again, if I have 100 unique values in segment and I'm looking for when one of these values is greater than something, I don't need to scan a million records. I could just go through 100 unique values, pick up that are greater than something, and throw away everything else. Third one is local aggregation. Sometimes it's called aggregation pushdown. It allows us to do aggregation on compressed data, and it's faster. And the next one is a compression. So data compressed, as a result, it's compressed in memory, it's compressed in on storage, so less I/O, less memory usage, faster operation. And the last one is batch mode. I will not talk about batch mode in most of slides after that, but basically, when usually SQL Server works with row groups, it takes one row and do operation, go to next. With batch mode, it's deals with a batch of rows. It's about 900 of these rows, as long as they are less than 64 kilobyte. And 64 kilobyte is important here because they can fit in CPU cache. As a result, when SQL needs to process that batch of data, it doesn't need to go to a main memory. It can do everything in a like with CPU cache, so it's improved performance a lot. Another part for batch mode that SQL Server can use SIMD CPU instructions. SIMD, it stands for single instruction multiple data, and it can give, for example, a list of values to CPU and say, just give me a sum as a one CPU operation, so it's improved performance a lot. So to have a good performance when using Columnstore indexes, you need to try to get as much of these 5 features as you can. If you lose segment elimination, you have not that good performance. If you cannot do predicate pushdown, you have even worse performance, and so on, so on. So when you design your data model and queries, how you query this, you need to make sure that you can use as much of this 5 as you can. Okay, so first lesson that we learned that data types are crucially important. I explained that how good is that we can aggregate the data, not unpacking them, but dealing with it is already pre-compressed form. But not all data types support aggregation pushdown. Our sample is we have a table called test result daily that contains test results, and for my test account, it's about 30 million records in this table. And I just want to sum how all these tests took during the day. So I'm using the select query. Excuse me? It was sound issues.
Nope, it's going through.
Yeah. Okay. So here is a sample. If I will keep duration seconds as a decimal data type with 18,3, I could aggregate 30 million records in 15 milliseconds. It's pretty amazing aggregating 15 million records with 15 milliseconds. If I do this instead of using decimal 18,3, I will just use float. My performance will be still good. It will be about 850 milliseconds, so it's about 60 times slower, but still not bad. And if you compare this to plans, you can see on a decimal version is very narrow line, and in float version it's very thick line. Why it happens? If I look in details, I will see for top one that actual number of locally aggregated rows is 29 million. So instead of unpacking 29 million records and doing 21 million sum operation, I just basically did 3 of them. So when you design your schema, first make sure that you pick data types that will allow you to do aggregation pushdown, or you will lose some performance. And rule of thumb, data types should be less than 8 bytes, and another one, it should be in list of supported. So SQL Server have a great page which says what data types support aggregation pushdown and which don't. Second one is cardinality of values really matters. When explaining how SQL Server stores this data, I said, oh, I have 100 unique values. But what if I don't have 100 unique values if all values are unique? In this segment, in this case, performance will not be so great. For example, we do have a column completed date that is data item offset, and if I have 1 billion data item offset for test results, whole storage for just this segment will be close to 6 gigabyte. And precision of this complete date is about 100 nanoseconds, so pretty good precision. But do you need to know exactly for 100 nanoseconds when your test finished? I'm not sure about that, so what we try to do, we decided to cut up to seconds. And after that, I have much better, smaller number of distinct values. It's still big, but it's 3 times smaller than I have if I have more precise data. But I can do one more optimization. If I will store only date part, I will not have as so many unique values. I will have pretty narrow set, and I will able to store my 1 billion of complete dates only in 900 kilobyte, and it's not typo, it's not 900 megabyte, it's 900 kilobytes. So between using data offset 0 and just storing the data as integer or as a date column, it will not matter. For this case, I'm getting 2.5 thousand x compression. And what this compression means for you? You have less data in memory, less data on disk, and less data to process when you run operation. So you get your pretty big boost on performance. How you can check size of Columnstore segments? It's pretty easy. We have a DMV called sys.column_store_segments that for each column, in each row group, so that is segment, shows how big this table is, and this segment is, you can analyze this segment and decide is it big enough, it's small enough, what we can do to optimize it. In addition to impacting the size, it still impact aggregation pushdown when you use group by. So if you use group by operation, we can still push down operation to a storage and do pretty fast group by. However, it's important how many rows you have. For example, I have a table with 3 row groups. Each one have 1 million rows. But columns that I'm looking for to group by for row groups number 1 and number 3 contains only 16,000 unique values, and row group number 2 have 17,000 unique values. If I execute this query, and we'll see how many locally aggregated rows will happen, it will be interesting data. So actual number of locally aggregated rows is 2 million, plus actual number of rows is 1 million. What happened? SQL Server is able to do to push down aggregation for first and third row groups, but need to do unpack second and do aggregation. So as a result, if you have too many unique values, it affects ability to aggregate pushdown, aggregation pushdown, and affect performance. It's not only one thing that affects aggregate pushdown, and in a deck, it's a link to a Paul White's blog post that have a pretty 500 deep discussion what can affect group by aggregation pushdown. It impacts how many rows you have, what data types it is. It's impacted by how they distributed, so which type of compression algorithm was used, and stuff going on, and stuff like that. Third lesson is predicate pushdown. So I want storage to be able to filter on compressed data as much as possible. So for this, I want to predicate pushdown. And again, it's some tricky parts. Assuming I have a query that says, oh, column A is equal to 1, or column B is equal to 2. In this case, it will be no pushdown because SQL Server have no way to figure out what overlaps between column A and column B, so it will be no pushdowns. If you have expression when column A is greater than column B, again, it's two columns that interact with each other. SQL Server have no information about this interaction, so no pushdown. It will need to extract whole segment, all segments for column A, column B, and do comparison row by row. Interestingly enough, if you use AND condition, it's kind of two independent expressions, so SQL Server able to push down for A, push down to B, and then do intersection for this. What it gives to it allow you to so what you can do about if you have expression like column A greater than column B. In this case, it makes sense to add one more column that represent a result of this calculation, and it says like A greater than B column, and filter on A greater than B column, and in this case you will be doing a good push down, and because you're not touching column A and column B in this expression, as a result column A and column B will be eliminated from a query, so you still have a good performance. Like, important to understand here that if you add more columns in Columnstore index, it's not always a bad, because your query will not touch columns that is not in your queries. One interesting part is string predicates. First, if you're using SQL Server earlier than 2016, it will be no string predicates push down at all. As a result, you will have not very so good performance. With SQL Server 2016 or up, you can have a push down on string predicates, but sometimes it makes sense to still deal like it's not happening, and idea is you can replace with a numeric code or surrogate keys. For example, if you have 15 unique strings, it makes sense to replace them with integer numbers or have dimension table and reference to it. It will give you better push down. Kind of related to this is string and segment elimination. Unfortunately, SQL Server so far doesn't know how to do segment elimination for strings. It's doing only for numeric values and for date time types. So no segment elimination for strings and for unique identifiers. In most cases, it's not a problem. Let's assume I have a work item tracking about my user stories, bug, features, epics, and other issues. And I have a query that filters give me only bugs. In my segments, I will have bugs in most segments because people report bugs, fix bugs all the time. So even I will have segment elimination for column work item type, it will give me nothing. So as again, in most cases, it's not a problem. If it's a problem for you when you have very specific distribution, I do recommend to replace them with numeric codes or surrogate keys. Again, create dimension, move your real strings data to the separate table, use join, and in this case, SQL Server will be able to do segment elimination on this stuff. Interestingly enough, SQL Azure DW, Database Warehouse, does support segment elimination already, but this feature is not yet ported and enabled for SQL Azure DB or SQL Server on-prem. Okay, segment elimination. Let's talk a bit more about segment elimination, and I kind of cheated at the beginning when I explained how segment elimination works, because it's for perfect case. For not so perfect case, it's not. It's a bit more difficult. Let's assume I have this distribution and I want to update rows. Because I need to update rows, my data changed. So for Columnstore indexes, update is delete plus insert. So what it means, after segment is compressed, it's no way you could modify it. But it does have special structure called delete bitmap that marks which rows were deleted. So when you run, for example, this update expression that will touch column C6, what it will do, it will find for all rows that need to be updated in original segment, it will mark these rows as deleted and insert in new row groups in new records will be inserted in new row groups. As a result, when you will do your sum expression exactly as was at the beginning, now it's need to read twice as much of data because we have old segments plus new segments. As a result, your performance will be not so good. So because you basically need to, it will go down 2 times. So as a result, when you're looking on segment elimination, try to keep this in mind, your update strategies, and make sure how many segments will be touched with each one query. So how you can deacon that and what you can do about this. First, in Columnstore segments, we have 2 columns called min data ID and max data ID that is encoded min and max values, so you can see which segments will be eliminated in any particular queries, and you try to optimize your data placement in a way that you do not have overlaps between different segments. So as a result, SQL will be able to select in one. So what affects segment elimination, what we can do to avoid this? First, try to avoid updates. So if you can just do inserts, do just inserts. If you need to update, you have to do, but try to avoid them. If you have a table that have a lot of updates and it's something that can use split in current table and history table, for example, we do have a table called work item history that have all changes in, for example, bugs. So what we split it into where is what is now, it's still Columnstore, it's have a lot of updates, so we need to keep an eye on it. But historical table, as soon as record is ready for insertion, it's moved to history, it's no updates here, and performance is better. By the way, if you using temporal tables feature in SQL Server, it will do exactly like that. You just will not be able to control the daytime ranges for these columns. Periodically, you need to check how healthy your Columnstore indexes, and if they're not very good, you will need to rebuild them, reorganize them, or do other maintenance procedure to keep segments placement aligned with your query strategies, so you have a good segment elimination. Another interesting part about updates is when SQL Server does compression. So when you insert data to a Columnstore index, it will first go to Delta Store. And Delta Store is a heap table with no compression, and it will be in that table till it reaches 1 million records. So what problem was that? Problem is whatever you have your placement of segments, each query reads whole Delta Store. And even if it was able to eliminate a lot of segments, it needs each time need to read whole Delta Store, and it can affect performance. And Delta Store could be pretty large. Let's look on a table that have like 100 of integer columns. Each integer column is 4 bytes. We have no compression, so each rows will have a 4 bytes, even if it's a lot of nulls here. 400 bytes. So compression will happen only when we reach 1 million records. So 400 bytes multiplied by 1 million, I will get my Delta Store can be as big as a 400 megabytes, and each query will read this big 400 megabyte Delta Store, processes in raw mode, and it will not affect your performance in a great way. As a result, you need to watch size of your Delta Store, and sometimes if it's too big and you do not have enough like rows incoming to start compression on its own, you need to force this compression. You can do this with alter index reorganize with special option force all row group, compress all row groups, so it will compress your Delta Store. But keep in mind you need to keep an eye on this Delta Store. Okay, so how physical partitioning affects this stuff? In case of our service with multi-tenant environment, so we do have a small accounts and big accounts. We could have some big account with hundreds of millions test results a day, and next to it, it can be account with a few hundreds or few thousands of test results a day. We need to decide how we store this in one big table. First, we could push all these tenants in one physical partition. What will happen in this case, small guys will be mixed with records from small guys will be mixed with records from big guys, and unfortunately when you deal with the Columnstore indexes, if you need to read a segment, you need to read a complete segment. As a result, for small guys it will end up that you read in segment million rows segment to extract 5 records and go for next one to extract another 5 records, so it's not very good from performance point of view. Another part, if you all these tenants write into the same time, it's only one tenant who can write to row group at any particular moment, because logs are not on row level, they are on row group level, so we have a problem here. And if you have a lot of data from multiple teams and they have a lot of unique value unique values each combined together, it have a too high cardinality, so mean less segment elimination, worse performance. Okay, let's give a separate partition for each tenant. Unfortunately, SQL Server limit us by 15,000 partitions per table. So if you have a database and you want to have thousands of small accounts, you will need have only 15,000 per database. And for our case, it was too restricted, so we have to do something about that. Another problem, small tenants will never reach 1 million rows, and it's more important. So they will stay in Delta Store. As a result, you basically have regular table with no Columnstore index for the small people. Performance will be really, really bad. So we need to do something. So As a result, what we decided to do, we use mixed strategy. So a lot of small accounts can go for one physical partition. Big guys with millions and millions of records have dedicated partitions. As a result, big guys doesn't affect small guys, and small tenants help each other to reach this this magical number of 1 million records, so they have a good compression. If you have a lot of physical partitions, you need to, and you have updates and other stuff, you need to maintain them. You can run index rebuild. Problem with index rebuild is that it will read whole partition or whole table and insert it in order that SQL Server will decide, and its order is kind of random. As a result, if you want to maintain your record placement in particular shape, you will have problem with this. So you might need to build a custom solution that periodically restores this proper order. So what we did, we built a stored procedure that doing this. It analyzes, oh, do I have a partition with a big, with bad house? And then it does this. It's quant stable structure. Then it copies data in desired order. It's doing it in 100,000 or 1 million records batches. As a result, it can be written to compressed row groups right away without writing to Delta Store. And it will work only if you use clustered Columnstore indexes. If you use non-clustered Columnstore indexes, it will write to Delta Store first, and then will be do compression. So keep this in mind. Then, when I'm done with major movement, I stop ETL for a while, so users still can access data, but it's not ingesting new data, some data latency here. Apply modifications and swap partitions. As a result, my customers always see data available. Sometimes I have some small data latency, but it's allowing me to maintain my tables in pretty healthy state. And because I need to deal with the small guys and big guys, I need sometimes split and merges to combine small tenants into one partition and split someone who reaches too many records. So split and merge process does the same. Another interesting thing is a schema update. So for any service, you will modify schema. You will need to add new columns. You need to recalculate something, stuff like that. For all services servicing in our service, it must be an online operation. If it keeps a log more than 30 seconds, it will be killed. For Columnstore indexes, it's tricky. If you just add most operations on Columnstore indexes are offline, so they are working. You cannot afford this. For example, if you add a nullable column or non-nullable column's default value, it's online and fast. But if you add in columns that you need to pre-calculate values, you potentially end up with need to update 100% of records. 100% of records means you will have 100%, like you basically double your data. All queries will read this double data. It's really, really bad for your performance. And so what we decided to do each time when we need to modify schema and it's require updates of data, so what we are doing, we create a new table, copy data with required modifications and swap tables. So basically it's the same approach when we do maintenance. And last lesson is how you deal with paging. So for our service, we encourage people to use it with aggregating data, but some clients like Power BI need just raw data with arbitrary filters and projections. And if I have tens of millions bugs, I need to do this with pages. As a result, I need to force this paging on server side to avoid overload. I cannot load tens of millions of records in one big JSON object and send to client. And here's a few problems. By default, when you build paging, you need to use multiple. You can use multiple approaches. First is to offset fetch or skip top, skip takes approach. What it means, I sort my data first, and then I say, okay, give me first page, first 10,000 records. Then next page, skip first 10,000, 10,000, get next 10,000, and so on, so on, so on. This require sorting, and problem with the sorting is that you need to get all data, sort it, and then throw away most of that. As a result, n+1 page is more expensive than page n. I recently did some interesting tests. I do have a table with 4 billion records. And first, to get the first page, it requires sorting. Is kind of decent performance. It's a few minutes because SQL have special optimization top and sort when it keeps only this size of page in top in memory. But when I need to get the last page, I need to sort all 2 billion records in memory, and it's a lot of memory. And as a result, it took me 22 hours to get to the last page. So from a few minutes to 22 hours is kind of big degradation. So offset fetch approach will not work here. Another skip, okay, we still need, so we pick some column that monotonically increasing, like identity column, as a pointer for next page. As a result, when I go to next page, I can skip most of data using segment elimination, stuff like that. It still will require you to do sorting, but it will each next page will be cheaper because you sort less and less and less and less data. But still, few minutes per page is not good performance, so we need to do something else. One of idea is, okay, I could try to avoid sorting. If I create B-tree, B-tree sorted data, I can go by B-tree and iterate this. It will break if I need arbitrary filters because I go by B-tree and I scan rows, skip rows that I don't like, bad performance. And if I already talked about sorting. So what we eventually decided to do a different approach. So first, I have two queries, leveraging Columnstore behavior. First query does that. It gets me page boundaries. So it eliminates more columns, keep only my columns in the filter, plus skip token. It uses aggregation. It still needs to do sorting, but it's much narrow side, so sort is not that expensive. It gives me a min-max for my next page. Second query goes data without sorting and says, give me everything between this min and max plus my filters. And because it's Columnstore, I have a good segment elimination because I eliminated everything before and everything after, no sorting, good performance. That's all that I have. So if you have questions, please let me know.
All right. Thank you, Konstantin. At the moment, we don't have any questions, but we'll give people a moment here to reply and ask any questions if they have them. This has been extremely useful. Some of the things I hadn't even really thought about that you were talking about there. So that was great here.
Sorry. So, what's the question? Or it's
no questions yet.
Oh, okay. Let's wait for a few minutes for questions.
Yeah, we'll give people a couple minutes to type in a question if they've got one. I do want to thank you while we've got the moment here. Thank you for presenting this today. This is an excellent topic and a lot of stuff that goes with Columnstore indexes that is not quite the same as a regular row store index, and it's always great to see those differences.
Yep. Thank you.
All right. Doesn't look like we're going to get any questions. Oh, here we go. Do you have a cheat sheet or bag of tricks that you can share?
So this deck will be shared. It's basically my cheat sheet of like bag of tricks. I going to start blogging about other more recent learnings not included in this deck. Like follow me on Twitter. We will see this updates for this deck. But this deck is the main source of this tricks.
All right, great. That is the only question we have. So thanks again. And if you want to get that deck over, I can link it to the meeting archive, and then folks can grab it from there.
Yeah, sure. Thank you.
All right. All right. Well, thank you everyone for attending. Thank you, Konstantin, for presenting this today, and catch everyone at the next presentation. Thank you.
Yep.
And goodbye.
Thank you. Bye.